To be talking to you today about something I love to talk about. And I'll be talking specifically about what I've been working on for the last year or so to implement the flow size and wave ice interaction model into the Earth system model of the community Earth system model at National Center for Atmospheric Research in the US. So I've been working with a ton of people, in fact, more people than who are listening today. Though I'm sure that by the recording, this will end up being heard even broader. But I'm really grateful to my co-authors. And I'm really motivated by images like this, where you see these incredibly small scales near the sea ice edge in the sea ice that I think are really important for influencing the climate interactions with ice. So the ice albedo feedback specifically, and I'll try to describe that as I go. But the basic gist of it is when flows are smaller, they have a larger perimeter, and therefore the proportion of basal to lateral melt shifts, and ice albedo feedback can be enhanced. Let me see if I can. Okay, great. So another motivation for me is how ice and waves are connected during high wind events, like major storms. And the evidence from images like this really suggests that storms can have a rapid impact on sea ice loss. And I think that a part of that is through waves, by fracturing the ice further, and probably also enhancing ocean mixing from below. And so being able to model this in Earth system models is really important. And you probably all know that the sea ice trends in our Earth system model are too weak. So specifically, we compute the trend for a given change in global temperature. The observed changes in global temperature that we see would give rise to much weaker sea ice trends. And so the only models that have sufficient sea ice trends over-exaggerate the global warming. So they can get the sensitivity right, the sea ice trends right, but they have to overdo the warming, which is clearly a problem. So we don't think that the actual sensitivity is right. And then another thing that's probably lesser well known is that the variability, say on 5-day timescales or so, in the case of this smallest frequency I'm showing here, the variability in observations is quite a bit larger than what we simulate in our system models. So that high frequency response to storms is also too weak in our system models. And like I mentioned in my introduction slide, I think a big part of this is because of lateral melt. So if you imagine a much more fractured scene of sea ice, the perimeter goes up. And when the perimeter results in a lateral ice to ocean interface, and there's sunlight absorbed in the ocean, if more of it gives rise to melt just at that lateral interface, that flows will shrink all the more. And that reduces the ice fraction and increases the open water fraction. So it's a positive feedback where we then absorb more sunlight. So it's a really important ice albedo feedback contribution that so far, when we don't resolve flows in Earth system models, has been utterly ignored. And that's the case. Like, no Earth system models have had flow sizes in them to date, though we are currently working on it in our developmental model. And another thing that I think gets under appreciated, although Luke did mention it yesterday, is that we should expect a degree of fracture, flow sizes, to influence the sea ice rheology. And that's currently not parameterized in our ice dynamics codes, but could be as we're learning how to simulate flows. So a major influence on flow sizes is from waves. We heard a lot about this yesterday, but just the prevailing view, is that wind on the open seas tends to create these high frequency wind waves, and those waves propagate into the sea ice, and the sea ice heavily attenuates the high frequency waves. And so what remains deeper into the ice is swell. And that's kind of the prevailing view. But meanwhile, all along the way, these waves are fracturing the ice into smaller pieces. And another kind of great cartoon was provided by Chris Horvat, where you can see kind of this cartoonish picture of waves coming in and fracturing ice. But another thing this shows is that the waves can also actually result in a stress on the ice that can cause it to shift position. So the last figure shows the last line, line 4 has the flows shifted through the stress effect. But then because there's more open water, you could also realize more ocean mixing at the ice edge, or even potentially some places inside the ice where there's larger openings. Another effect is through the growth processes. When there's more waves, the new frazzle ice formation tends to coagulate into these pancakes. And so with higher waves, we expect more pancake-like formation, and with fewer waves, it would be more flat, like a nihilus type of growth. And then some of my newest work I'll get to, hope today, is on how deformation influences fracture of ice. So deeper inside the ice, probably far further than we would expect wave propagation, we still see flows, and those flows are probably determined from the fracturing from deformation. So diverges and stress on in the ice velocity field can give rise to fracturing, and you can see kind of indication of it here further into the ice edge. It's just really for motivation to see a picture like this. So I'll get to this when I start presenting results today. But some of the model requirements to simulate these things are mechanisms of ice fracture, both waves and deformation. In turn, the impact of ice on wave attenuation. So we need to have a coupled approach where the evolution of the ice in turn affects where waves are and how they're attenuated, and then to simulate the flow sizes, because the way the attenuation plays out is a function of flow sizes, as is many of the things that I'm interested in, like ice albedo feedback and the rheology. So we need to represent flows and waves and their interactions. And as I mentioned earlier, no Earth system model has done this before. There's at least one Earth system model that I know of that had waves, but they did not go into the sea ice at all. So they had no ice wave interaction. Now, what I did many years ago in SEIS was put in a placeholder for a flow size model, but I set all the flows equal to 300 meters in diameter. So that's fairly large, and we don't think that would give rise to very much ice albedo feedback. I kind of chose a conservative value, so it didn't. And now we can compare with that older method of just setting all flows to 300 meters, which I'll do in my talk today. So we're simulating what we call a joint flow size distribution in the SEIS model. And so that's represented by this quantity F. And it depends on transport, and then these three terms that kind of include some multiple mechanisms, in especially the thermodynamics. So the thermodynamics is a combination of how flows are affected by new ice formation, lateral melt causing them to shrink, and growth causing them to grow, and then flow welding, which when there's freezing in the waters between flows will weld flows together. And then the two major fracture mechanisms are waves and deformation. So we basically step through each of these processes separately in our code. And unfortunately, I don't have as many great results from simulations. I do have some, but the work that I've mainly been doing is to bug fix and to tune the model. So I wanted to actually say what the bug fixes were, because I think some of you are using SICE and may not know about all of them. So you definitely want to be keeping up on the updates to SICE and IcePack specifically, where the flow size distribution code lives. And a minor code change that was necessary for conservation was in the new ice formation, and that's a recent update. A more major update was to lateral melt, and I had that added to IcePack about 19 months ago or something like that. So it's been around for a while, and but it had major consequences for how this code works. And then within the last few months, a really major change to the welding scheme. So don't hesitate to get new code on a regular basis as it's so rapidly developing. So I will be showing results now from simulations in this CESM3, the developmental version of CESM framework. It's a fully coupled model, but at this moment I have taken out the atmosphere and used prescribed atmospheric reanalysis. That's just for simple practical reasons. It runs faster. It really has no well, let me rephrase this. It won't be a big stretch at all to switch to a fully coupled atmosphere. It's just for efficiency at this point. But everything else is in place with a full wave watch model and MOM6 for an ocean model. And I'm using a 2/3 tripole grid for this, which is a nice grid because it doesn't have any poles in the Arctic in the model grid. And it includes the joint flow size distribution in SICE with all my bug fixes. I'm using the wave attenuation scheme from Melon et al. 2021. And I've been developing some improvements to the wave watch scheme too that I'll talk about a little bit today. And that was really motivated by some results from Vince Cooper and some of us a few years ago, where we were looking at observations of waves, and these are in the Arctic Ocean, kind of north of Alaska. And what we saw was that pretty deep into the ice, say 100 kilometers plus, we were seeing these really high frequency waves. And this is in the wave spectrum, so wave energy is measured. And we didn't expect that. And in fact, the longer frequency swell is more attenuated than you might also, I mean, you might have expected the opposite. So our expectation was really to see the wind waves be heavily attenuated, and what would be left would be more swell. And we don't see that anywhere. And that really suggested that, in fact, there's a lot of wind energy introduced in the marginal ice zone that may need to be rethought. And in terms of how little ice, or sorry, how little open water can still allow wind wave to be introduced. So that was part of it, but another big part of this research proved that there was some numerical issues with wave watch that would really help not attenuate these waves so rapidly in the ice for numerical reasons, not for the physics that we had thought we were coding up. And that comes down to the fact that the wave action energy spectrum is coded up is through this quantity n, and just ignoring the transport for now, it depends on sources in the ice and unrelated to ice. Is it possible for the people online to mute, because it's actually kind of distracting to me to hear the background noise? But anyway, thanks. I'll carry on. Anyway, the way it's coded is to split the effects, and there's a no CI source in solution that comes to an updated value for the wind energy or the wave action energy. And then second to that, the effect of the attenuation in ice has its own contribution. And normally this would make no difference, except that there's this extra little epsilon here, and that is where all of the subtlety of why this matters sits. And that epsilon sits on this extra term that makes for a semi-implicit solution to the first step. And if epsilon is a half, it's a second order accurate solution. So it's a nicely coded, nicely chosen numerical solution. But I won't go into all the complications unless for some reason I have extra time at the end. But it worked out that if we actually combine this source back into the first step, we got a much more accurate solution. And the main reason is because this quantity d, the derivative of the source with respect to the wave action energy, is more positive, and that's sorry, less positive. So when it's positive, the epsilon would actually go to zero, and this would revert to this kind of forward Euler solution. So it does that much less often, and so it's much less numerically damping if we combine them. And so I'll show what that looks like next. And with this combination of terms, instead of separating them out, now we're getting much higher significant wave heights in the ice. And that is purely from a numerical choice. It's something like 50 centimeters higher at times. And wave heights of that magnitude in ice are pretty devastating. So it really fractures a lot of ice. So an easy fix, and it also makes a big difference when you have these wind waves that are occurring simultaneously. So when wind waves are being introduced into the ice simultaneous to attenuation. So I'll show you some more specifics of kind of locally what that looks like. In, say, like the Greenland Sea, I've just taken a transect through where there are flows in, as you can see in this MODIS image. And before I made any changes to WaveWatch numerics, it was reasonable that we were simulating these flows of a couple hundred meters, though this is the representative radius, and the actual representative radius may be a little bit higher here, but it definitely has the kind of characteristic fall off at about the right place, and the significant wave heights are on the order of a half a meter, right off the eye, where these flows are really small. Now, when I improve the numerics, the original are in, sorry, this is, the previous one was the improved numerics. Now with also showing the original numerics, you can see we had less wave magnitude in the ice as we were over damping those waves, and so the flow sizes were a lot bigger, and really substantially changing the solution now. And if you look at what this looks like in a spatial map, it's with the improved numerics on the left, far smaller radii and of flows, but also much greater wave heights in the ice, and the action is right specifically at the ice edge usually, but in places where the ice concentrations are low, such as here, you can really see a major difference between the two simulations. Wanted to just talk a little bit now about the basic terms that give rise to radius that we simulate. And the image on the left is the average radius at a given point, which we call a representative radius. It's the first moment of the flow size distribution. And of course, I've also added the old definition of the marginal ice zone. This was discussed at length yesterday, and how those do differ. You don't really see small flows only in the marginal ice zone. Sometimes they exist within the ice pack further in. And the major contributions to what gives rise to the evolution of the flow size distribution is really primarily depends on the time of year and where you are, but a lot of new ice growth making small flows, and then wave fracturing the small flows, and fracturing the medium-sized flows and making small flows, and then welding, combining the small flows, so removing small flows and moving them up into larger flows. And I think this wave fracture was too excessive, so too efficient at just fracturing the heck out of these small flows and putting them all into the smallest category. And others are working on doing that more realistically. But such as it is, this is what results look like, with first on the upper row, the effect of having a uniform flow size distribution, and how much lateral versus basal melt that we simulate. And this is in January, so it may surprise you. There's actual basal melt at the ice edge in January, but it's not unexpected because of the transport from regions of growth out to the ice edge, where it meets warmer waters. But once we start to simulate a flow size distribution with flow sizes that are small at the ice edge, we get much more lateral melt. In fact, more lateral melt than basal melt, and ultimately less sea ice concentration in those regions. It also has consequences for sea ice thickness, with generally a reduction in the thickness with the flow sizes that are resolved, compared or parameterized relative to this 300-meter uniform flow size. So the last thing will be to talk for a minute about adding this new deformation schemes, and none of those previous figures had the new deformation fracture in it. So I'll just show the sensitivity now. So we've just added this. And the aim was to try to deal with some issues with the flow size in our simulations. Earlier work from Letty Roach showed that we had a tendency to produce a high number of very large flows, this kind of tail at the end that we don't feel is very real. It's not realistic. It's not what's observed. I think it's partly there because of a truncation error, just in have to stop resolving the flows in the flow size distribution at some point. And but I think also we weren't shifting flows from these highest flow radii fast enough. And this gives rise to a lot of very large flows in the Central Arctic, where now with a new added deformation scheme, where we have deformation in the interior of the ice beyond inside the marginal ice zone, that gives rise to changes in the flow sizes. And these are SAR images 1 day apart after a deformation event. And you see these new open water areas, and that gives rise to smaller length scales within the ice of continuous ice. Niels Hutter has figured out how to quantify these, giving a before and after. And this is a chord distribution, which we then subsequently transform into a flow size distribution, and then calculate the change due to a deformation event. And when we coded that up and added it, it does exactly what we expected, which is to eliminate a lot of these really very, very large flows and shift them to smaller values. So that in turn has the biggest impact, like I said, inside the marginalized zone, and it sort of halves the representative radius, especially in summertime in both hemispheres. So in summary, we're modeling the flow size thickness distribution in Earth system models now. These are simulations that are about 1 degree resolution, coupled to waves and other Earth system components. We're still really in the testing and parameterization tuning phase. I think we have the basics all in there, but we have some work to do to get this in a perfect form. But I'm particularly excited about this new deformation fraction scheme. The model still, I think, has a problem with the flows being too small in the marginalized zone. And so I think we do need some work towards improving how we deal with fracture. But that said, that gives rise to a lot more lateral melt in the model and probably higher albedo feedback, which is going to have impacts on trends and how sensitive the ice is, not just to climate forcing, but to short-term weather kind of events. And I really needed to improve Wave Watch to do this work, and I'm happy to talk more about it if anyone's interested. Okay, that's a good place to stop, I think. I'm at my time and I'm happy to take some questions.
Thank you very much, Cecilia. Chris already have a question.
In the chat?
Hey, Cece.
Yeah.
Can you hear?
Oh,
No, I'm just. Can you hear me?
oh,
Okay. Sorry, I think
yes,
that
I
was
can.
me that was unmuted earlier. So apologies. I hope I didn't do anything embarrassing.
No.
Yeah, I had a question about, well, two things. First of all, the work that you and Niels have done is really cool. I mean, I think that's yeah, identifying that was such a problem for the early papers. So it's really neat that's working and does something interesting with deformation. That's just a comment. But the question I had is, have you or anyone else run coupled simulations with an FSD? There's not a lot of instances like that. And I'm just curious, because of the impact on lateral melting, whether it has any effect on things like overall sea ice area sensitivity or something like that.
I have, and I got a little burnt because it was 2 years ago and the clouds were still not very settled in the scheme. And so anyway, the bottom line is it was exhibiting unreasonable climate trends that had nothing to do with what I was doing. That, you can still maybe take the difference between two simulations and hope that you're seeing what you aim to. And when I did, yes, I definitely saw a substantial impact. In fact, higher trends due to smaller, simulating flows. And then also, I thought this was kind of cool that I was able to see higher variability in the 5-day periods of sea ice variability. So, extremes were higher in sea ice loss events. So, yeah, but I'm not ready to publish those results because the model was kind of drifting too much.
Thank you.
Gotcha, thanks.
Juan Lim.
Yes,
Yep.
thank you very much for the very interesting presentation. I really enjoyed it. In particular, I'm really curious about the numerics part. And you mentioned that without the fixed, the convergence rate is like half. Where after fixed, what's the convergence order? Like, is it order 1? And the order, in what sense? In the sense of space resolution or in the sense of the time sizes?
I'm not sure what you meant by convergence, but I it depends on the time step. And these coarser resolution models use a large time step. So our time step is 1800 seconds. So it's out here.
Yeah. Okay.
And one thing you can do is subcycle. And so that's what we actually have implemented, but I don't think it's necessary.
Yeah, so I mean, like at the end of the day, this is just a PDE or to solve, right? And there are so many very nice numeric methods so that it can avoid, like, say, numeric dissipation or any other things like high order time integration methods, like
Right.
generalized alpha method can be potentially applied here. So if this numerical method is improved, will this result be further improved, or there's no room to improve at all?
Well, I think that there's room for that, but this semi-implicit scheme at least is second order accurate, and the fact that it's implicit means it should be nice, more stable. But the bummer of it was that they eliminated the second order accurate term or this higher order accurate term by any time the the wave energy amplitudes were growing. So that's where I think the problem lies. And I know why they did it. They did it because they found the model was too noisy. And so by eliminating this more accurate scheme, by reverting back to forward Euler, that's very numerically damping. And so they damped a lot of noise that way. And so in our case, by merging these two influences back together, the no ice and ice, into this one combined D, if you like, because ice is always attenuating, it makes the overall value of D smaller. And so you utilize this, this term more often, right? Because you have less occasions when you have
yes.
high magnitude amplitude growth. And so it ends up being that you just benefit from the numerical accuracy afforded by this clever scheme more often.
Yeah, so what if on the left hand side of these equations, if you have like a high order time integration methods like the second order, would that, like the curve that you showed, will be much different?
I think, I think the goal is to, of course, simulate the exact solution, and we already are close to it. But I'm sure there are many other ways to do it.
Okay.
And,
Sure. Yeah. I mean, there are oceans of very high level time integration method. It's in computational mathematics. There are so many nice methods. I'm just curious, like if this is actually useful.
Yeah, I didn't totally change it because I figured I would get more traction at people being comfortable with the change if it was a modest change, right?
Yeah. Okay, sure.
Yeah.
Thank you very much. Thank you.
Thank you. Ian, one last question.
Hey, good morning, Cece. I really enjoyed that talk. Nice way to start the day. There's so many interesting things here, but I wanted to ask you something really quick, actually from the introduction, although you circled back to it in the conclusions. You showed that the spectrum of variability as a function of frequency in observations and in CESM.
Yeah, I didn't show it in CESM. Sorry about that.
What was that? What were those two spectra?
Those are both in buoys. Is this one you mean?
No, I mean the one that said power versus frequency in it. I thought it showed that that NSIDC data had a
that
one went right before
Sorry.
it. This one.
CI spectrum. Sure.
Yeah, so I was just okay. Sorry, I'm looking back. Yeah, so I was just wondering I like your mechanism that this has to do with flow size distribution missing from CSM large ensemble. And I guess the thing you showed in response to Chris's question gave a hint that could contribute. But is the atmosphere culpable here too? Has anyone compared this with what happens when you have, say, a specified reanalysis atmosphere?
Stratified reanalysis atmosphere, did you say?
Specified, I'm sorry, I'm mumble in the morning.
Specified
reanalysis atmosphere.
Well, that's a good point. Yes, we did. And it's been too long. Can't recall. My recollection is it doesn't matter. If you look at the low level winds in this model, they're actually higher energy. They have more variability at synoptic scales. So I don't think the model's atmosphere is anemic, if that's basically what you're asking. So, but I'm sorry, I don't have that.
Sorry, did you say emic?
Anemic. Weak.
Anemic. Okay. Got it. Okay.
Yeah.
It's fair. Thank you. Thanks a lot.
Yeah.